Log on, tune in, find out. Another good idea from Cambridge.
Speaker is Gideon Schechtman from the Weizmann Institute. What is the title?
I'll speak about embedding of subspaces of LP in little LP of small dimension.
Turn up the mic.
I think that I did. Turn on. Maybe I'll put it here. Is it better? Should I shout? No. Okay, so I'll speak about embedding of subspaces of LP, finite dimensional subspaces of LP in little LP of as small as possible dimension. And I have some specific new result, which is actually very simple. So, which means that I have a lot of time, so I'll talk about a lot about the background and history first. So first of all, for me, when I speak about LPL, I prefer to speak about the infinite dimensional LP and actually capital LP of 0, 1. But I don't know, I know that many of you come from the discrete world and the finite dimensional world. So for all practical purposes, you can replace this with little LP M, but with M finite but unrestricted. Okay, you'll see in a minute. It's just, I prefer to speak it like that. So of course, but this is just a space of all functions on 0, 1, such that the integral of f to the p with respect to the Lebesgue measure is finite, and this is a no. Okay, so I'll speak also not only about Banach spaces, I'll speak also about p smaller than 1. So, but this is well defined. Then it's not a Banach space, but it's still a metric space with this metric. And so, given a subspace of LP, okay, so I should warn you, I'm probably the first lecturer who will speak only about almost only about subspaces, and embedding for me are linear embedding, not Lipschitz, not anything, even though I'll say some things about that. So this has been denoted by LP. X is finite dimensional subspace. So the main subspace, not subset or anything. And I'm interested in, and in that case, it's very easy to see that you can actually embed it in LPM. I'll say in a minute what I mean by embedding. For some finite m, depending, actually m can be only a function of the dimension, but in the simple way of doing it, the dimension is, the m is exponential in the dimension of x, and I want to get much better results. So let me define kx and, no, I call it nx and epsilon. That might capital N. Okay, I'm sorry. Capital N, and depending on your p of x and epsilon, will be the infimum of the of n's, such that x embed 1 plus epsilon embeds into LP of dimension n. So what do I mean by that? So when I have two Banach spaces, two norm spaces, say, I say that x embeds with constant k and y. This is the same as this by definition is the same as there exists a linear operator from x to y, such that the norm of so t is linear. I emphasize this because it's a k isomorphism, namely you can always choose it like that. Everything is homogeneous, so, well, you can always put the k on one side. Okay, this means that x k embeds in y. Now, if you, I know that many of you like the Lipschitz word, for when you speak about norm spaces, and to say this, this is the same thing as K-Lipschitz embedding. If you have a Lipschitz embedding, you can always linearize it by differentiation. When you speak about, I'm speaking only about finite dimensional spaces, so there's no problem of differentiation. So it's really the same as Lipschitz embedding, but for linear spaces. Okay, so this is really the thing I'm interested in. Give me a subspace of LP. In what little LPn can I embed it nicely? And I'm speaking about, I'll think about epsilon as a small constant here. And let me also define npk epsilon as a maximum, so as a maximum of npx epsilon over all x's of dimension. So x is a subspace of LP, and the dimension of x is k. Okay, so this is the worst, the thing that you get for the worst subspace of dimension k. And now this was a topic that was studied a lot for, well, actually starting with Dvoretzky theorem, but mostly, I mean, for x's other than Hilbert spaces. I'll speak about it in a minute, where Hilbert spaces enter here. It was studied a lot in the 80s mostly, and there were all kinds of results. And let me first state the best known results until a few months ago. So best known estimates until recently. So it depends on the value of p. So what is known is the following. So np, I'll speak about the second thing, but okay. So this is smaller equals than some constant. The constants always depend on p and epsilon. I'll say something about the constants later on. And then there is a different behavior when p is larger than 2. I'm always speaking about p smaller than infinity. Infinity is something special. I don't want to speak about this. Well, so here you get something of the something like k to the p over 2. So as I said before, it's easy to do it with this thing with a dimension exponential. The dimension n's are exponential in k, but the point is that you can do it polynomially depending on p. Unfortunately, it's known that you cannot do better than that. I'll speak about this too later. Unfortunately, it's not exactly known what I wrote here, but only with some log k, I think. And for p smaller, there are really many different results here by different people, but I'll combine them all. In the range p between 0 and 2, you get something which is quite surprising to somebody who, I guess, who didn't see it before, something which is almost linear in k. So k, and again, there is some log factors. It's really what is best known is log k. I think, I'm not completely sure, log k squared, I think. Okay, anyhow, some log factors, log k times log k squared. I think that this is the right thing. And the best results are, so this thing is by Siegel, Lindenschloss, and Millman, Bourgain, Lindenschloss, and Millman. And this one, it depends on the range, is, let me say, p equals 1, there is something a little bit better, which is just k log k. You can remove the, but the nice thing about this is a nice proof more than anything else. But okay, this is by well, the way it is written is by Talagrand. Bourgain, Lindenschloss, Millman had some other factor of log. So this is by Talagrand. This is by Talagrand. I'm sorry, this is by Talleyrand. This is by Talleyrand for p larger than 1. And by Zvavich and myself for p smaller than 1. And t equal 1, there is another proof of Talleyrand, which is a little bit better. So these are the best things that were known until very recently. And the main problem here is are the log factors necessary? If not, without the log factors, it's known that these are best possible. Here, of course, there is nothing to speak about. You need at least the dimension of the space X just from dimension consideration. And of course, there is also the problem with the constant. There are all kinds of problems with the constant. I'll not talk about it, but I'll talk about it a little bit. But the main problem is the dependence on K. And let me just say that it is known that, so in this case, it is, so for, I'll write it here maybe, something which is not trivial, that for p larger than 2, np k epsilon is larger or equal than some constant, depending on p and epsilon, maybe, I'm not sure. Well, some small constant depending on p and epsilon times k to the p over 2. Okay, so this power of k is the right one. And this is due to Bennett, Dorr, Goodman, Johnson, and Newman. Okay, so, and this is not trivial, even though the proof is not very hard, but it's kind of clever. Okay, so the problem is really with the logs only. And the thing that I'm going to speak about later today is I'll show you that one can remove the logs in this case for even p's. Okay, and okay, but before I come to that, I want to say, okay, so this is best as is known, but I want also to speak a little bit about the history again because I have time, and I want to say something about how these things were achieved, and especially where were the kind of breakthroughs. So this is a history with, I'll call it history with.
Can you state explicitly what is known in the case in the next one?
Yeah, so very little is known. So for p equals 4, it is known that you can embed. So so what happened for epsilon equals 0? So the only non-trivial thing that is known is for p equals 4. So it's known that I'm sorry, and not for a general subspace, but only for a special subspace, for X being L2. For a general subspace, nothing is known. But it's known that L2K embeds.
I think it's for general substance, it's impossible.
That what? That it's impossible. It's impossible, I think. Yeah, I think it's.
You always find a subspace for which you could not Weizmann.
Yeah. Yeah, there are, for general subspace there is no chance, but for L2K, which is the most interesting case, this embeds into L4 of dimension approximately k square. I mean, you can write some constant times k square, okay? And this is isometrically. There is also, for the other even p's, there are also some results known, but the power is not the right one. It's not p over 2, but actually doubles it. It will be p. So it's also known that L2K, 1 embeds into let's say 6, but of dimension should be 3, but you get 6. It should be k to the 3, but you get k to the 6. Okay, so, and it's not known actually if you can do it into k to the 3. It's known that you cannot do better, but okay, so there is some, but this is the only case that is really completely resolved for isometric embeddings. There are also issues of the dependence on epsilon, which is nice if you don't know the isometric embedding. I'll speak a little bit about it because the proof that I have gives some better estimates than what was known before. Okay, so this is a history with some personal bias. Maybe. So it's really, I mean, I think, as I said, it can be traced back to Dvoretzky theorem and mostly to theorem of Millman. So this is mostly Millman, which gave a different proof of the Dvoretzky theorem, but it gives also all kinds of special things. So this is Millman 71, basically. So it's not written there, and it's really written in a paper by Figelin, Jose Millman, from 77, I think. I'm in England, so I should write 7 here, like that. That the case of L2 is, so maybe I'll write it NP of L2K. So I should say little L2 embeds isometrically in all the LPs. So it is an example of a subspace of LP. And probably the most, except for little LP itself, maybe little LPK itself is probably the nicest thing. So he proves that this thing embeds into that this thing is smaller or equal than a constant times k to the p over 2 for p larger than 2 and k for p between 1 and 2. It didn't deal with p smaller than 1, but actually it works, the proof works also for p smaller than 1. Okay, so this this completely resolved, and these are best possible. So again, the first one is best possible is in this paper of these 5 authors. And this resolves the case of x being L2k, except maybe on the dependence on the constants. So once one sees that, so in particular this says, let me first speak about p equals 1. So the case p equals 1, which is probably the most interesting one anyhow. So you get that L2k embeds into L1 of, I don't know, some constant times k, constant depending on epsilon, which is very strange actually. L1 is kind of what it says geometrically is that if you look at the ball of L1, which is, excuse me? No, little l. Finite dimensional little L1, the dimension is, okay, dimension is a constant times k. The 2 is not k. Okay, so this is a, so this L1 ball, the ball of L1, which is, you know, has a lot of edges and I don't know what, there's a section of dimension, of proportional dimension, which looks like the sphere. This is what this thing says. And then one can ask, okay, so what are the other large dimensional sections of the L1 ball? Are there other ones which are kind of nice? And this is something that Bill Johnson and I thought about, and we proved, this was 82, that the same thing happens for LP. So for P between 1 and 2, so you should know, let me write it, LPK embeds this constant 1 plus epsilon into L1 of C. The same thing, except that C now depends also on P and an epsilon, okay? So this strange ball, this ball of L1 is a section which looks also like the LP ball for every P between 1 and 2. I should say that it was known that LPK embeds in capital L1 isometrically. This is actually comes from this is proved using p-stable random variables, so it's really due to Paul Levy, who I think the first one who introduced p-stable random variables. Okay, so this is again, this is another example. It's an example of a subspace of L1, actually non-trivial example of a subspace of L1. This is not true for p larger than 2. For p larger than 2, LPK does not embed into L1 with uniform constant. Okay, so, and I want to say something about this. I mean, because almost every step here had some kind of a new idea or something, you had to change the intuition or something. We actually, Bill and I actually tried to prove that this is not the case, this is not the, and the reason is, so I'm talking maybe a little bit to people who know something about this. The way one proves the embedding of L2 is by using concentration, and so you can use it, for instance, using Gaussian random variables, which have exponential decay, and it's very, even square exponential decay, and this is very important in the proof. You use concentration techniques, which is really the contribution of Millman for that. Now, the way LPK embeds in L1 is using p-stables, as I said, and p-stables have only polynomial decay. So one expects that nothing like that should work, and actually what we were trying to do is actually use the fact that p-stables have only polynomial decay to show that this does not happen, but somehow we were led to a proof of that. And by the way, the strange thing is maybe that the proof uses p-stable random variables, but we kind of truncate them and do all kinds of things. Okay, so I don't know, it was kind of a, okay. The next thing in my list is a,
You know, and there is a remnant of this phenomenon, which is still an annoying open problem, but it's p tends to 1, your c
yeah, right. You're right. So as I said, this constant depends on p and epsilon, and it deteriorates when p tends to 1, not to 2. To 2 it's okay, but when it tends to 1, it deteriorates, and of course L1k embeds in L1k. So it looks like something is wrong there. There should be another proof. There should be another proof of some other variables used in this or something like that. Certainly, yeah. I completely agree.
The way you formulated the question, is there any chance of telling which sections this has, or that's?
These sections L1 have?
Yeah, is there a role for a general?
Yeah, of course. This is what is written here. You see, any subspace of L, this is what is written here. Any subspace of dimension k of course, there must be subspace of capital L1, because there are going to be subspaces of little L1 of dimension k. So what this thing says is that every subspace of capital L1 of dimension k embeds in little L1 of dimension c times k, except for the log.
Does this exhaust all the possibilities?
Right, sure. Except of course, for I have the problem with the log, but
it's only a question of dimension.
this is exactly the.
What's your view about the log now? Are you still?
My view is that it is not needed in view of what I'm going to speak about. Like, I'm going to remove the log in this case when p is even. Okay, so I guess it's not. And actually, the way I reach this result, which is very simple, you'll see. This is why I'm dragging on. Is that I was trying to do it really for L1. I couldn't do it, but I have kind of a feeling that something similar should work for L1. Okay, so I'm really going too slowly, I think, even for. So let me be a little bit more quickly with the history. Then in the 80s, I had several. I just tried to do I tried to do this general thing for a general subspace of L1, and I had all kinds of results. They were also all in they were in both ranges, and I got all kinds of polynomial. I will not specify exactly what, but polynomial estimates for this npk epsilon in terms of k. Okay, not exactly this, but some other powers. Here it was, for instance, p over 2 plus 1 or something. And this was also a surprise for me. Also, when I worked on it, I was sure that I was trying to find a subspace for which the estimate is only exponential, but somehow, and I had some 3 or 4 papers on that, and they become more and more complicated. All kinds of truncation of p-stables, strange things, truncation of p-stables, and all kinds of things like that. But finally, I came up with a very simple way of doing everything that I could do before in a paper in 87, and this was a completely different embedding. And let me describe this thing. This was just something which looks very simple, maybe. So we have this subspace of LP. So there are some functions. This is a space of functions, and there is one way that you could try and embed, and this is by just sampling some points on the interval, and look just at the, so take one function and just look at the value of the functions on this point and normalize it properly and think about this as an element of, so you sample n points, this is you look at them as a vector in LPn and you compute the norm and you hope that that the discrete LP norm here kind of approximates the LP norm here for all subspace in your subspace, okay? And the only way I could think about picking the points is by just sampling them according to the Lebesgue measure or whatever. But of course, this is very naive, and of course it's completely wrong because your subspace may consist of functions which are all supported on some very small interval. I mean, all your functions are here. Can be very well, and this is really the case why I wanted to speak about capital LP. And then if you sample, you can completely miss this interval, and of course nothing will happen. So the point in this paper was that you can first do some pre-processing. So you take your subspace and somehow apply some linear transformation on it so that the functions do not look like that, but they are kind of spread out as much as possible. And then you do the sampling. And this turns out to work and give something, not give the, as I said, it doesn't give this result, but it gives it with some other power. It's quite close to this, actually. And then the next major step was this paper of Bourgain, Liederschloss, and Millman, which took this idea and did the estimate better using entropy, which I didn't use. And they got the right result. So this is the way they got this, and also got here similar results, a little bit worse than what Talagon got later. Okay, so this is what I want to say here. There was this sampling, I would say, sampling works, which is quite surprising that it works. I don't know. Okay, so this is, there is some more, the history goes on a little bit more, but I'll stop here, I mean, because I think that these are the major steps. There is also this special paper of Talagram just about L1, which is very nice, but it's really... Okay, now, let me, because of the audience here, let me say something also about Lipschitz embedding of a subset of LP in little LP n. Then of course, if you have k points now, not a subspace of dimension k, if you have k points and you want to Lipschitz embed them nicely in LPn, then you can look at the span of them and use what is written here. And strangely enough, almost nothing better than that is known. Okay, so there is something a little bit better. Here, for instance, you can remove this, and so. Well, I'll speak about lower. First about the upper bound. Okay, for the upper bound, nothing much better than that is known. There is you can remove these things, and there are, and actually the proofs. You can use this paper. This paper actually contains almost everything that is known in this case. So you don't need the more sophisticated ones for that. So there is a simple proof which gives basically these things. As for lower bounds. As for lower bounds, we don't know. We basically don't know. And also, let me say that for p equals 1, there is now for p equals 1, one can now remove the log k. This is a recent observation of Newman and Rabinovich, which I may speak about. It's very closely related to what.
You know, the pre-processing is an isometry. The one you do.
The pre-processing is an isometry actually on all of LP, not just on the subspace. Yeah. It's a change of density, what we call it. I mean, so it's really what you would do in such a case. You would kind of spread this interval to all the interval. I mean, you can spread everything evenly. But of course, in general case, it's more complicated. It depends on a lemma of Lewis called change of density lemma of Lewis, which also originally was not so simple, but there is this is the main contribution in this paper of Zvavich and myself, that there is a kind of an elementary proof of this lemma, which works also for p smaller than 1. So the key word is change of density. And actually, if you if you speak about the nonlinear case, I mean embedding just k points, then this is probably the thing that need to be, I mean you need something different if you want to improve the, with this change of density you cannot do better than, say in the L1 case than k. By sampling you cannot do better than k, it's clear because you have to hit all the, I mean they could be, the k points could be disjointly supported and you must hit all of them, so you need at least k points. So it's clear that you cannot do better than k with sampling. So in the nonlinear case, you need something else. And by the way, this is the only linear part in this proof. I mean, this change of density, everything else is. Okay. So as I said, for k points, you can now remove the log k, and I'll maybe speak about it at the end. But this is all. I mean, we don't know anything better. Of course, for p equals 1, there are lower bounds. For p equals 1, there are lower bounds which are of polynomial type, n to the constant over the distortion square thing, yeah? Due to originally to Brinker and Charikar. And there are easier proofs of Lee and O. Okay, I'm not going to speak at all about the nonlinear case, except that maybe I'll say something about the Newman and Rabinovich thing. Okay, so the new thing that I can prove now is the following. So if p is an even integer, then I need some technical thing, but it's really needed. And k is larger or equal than p, then npk epsilon smaller equals than, I'll write it very precisely, epsilon to the minus square, a constant, some absolute constant over p to the p over 2, and then just k to the p over 2. So the main thing is that there is no log here. It's really k to the p over 2. There is some constant depending on p. And one thing to notice is also that it actually improves with p. Okay, when p grows, it becomes smaller, this constant. I will say something about this later. But the main thing is, of course, the removal of the log. Maybe let me state it differently because I want to compare it with other results. So
C depends on P.
Excuse me?
C depends on P. It's independent of P.
C is the absolute constant. It's 10 or something like that. I mean, actually a small constant. Let me write it differently. I mean, change the role of k and p. So this says that any k-dimensional subspace of LP, 1 plus epsilon embeds in LPN whenever k is smaller or equal than some absolute constant epsilon to the 4 over p, p n to the p over 2. All I've done is just call this n, and I kind of wrote an inequality for k instead of okay, so why did I write there? Why did I write this? Because I want to say that there is some other thing here which is interesting maybe. First of all, there is, as I said, it improves with p.
2 over p. Is that right?
2 over p
Here?
Oh, then.
Yeah, 2 over p. Thanks. Yeah, thanks. Okay, so first of all, it improves with p, but this was known before, actually exactly the same thing. This is, wait, I'm sorry. No, it's wrong. What I want to say is that this gives something new even for L2K. Okay, not just a general subspace, but even for L2K. So for L2K, what was known before was this additional p here, which did not appear in the theorem of Millman. It was known that this appears. This is something I noticed a long time ago. And well, let me tell you what. So for L2K, what was known was that something like that was a constant epsilon square n to the 2 over p. So, and actually, I'm sorry, there was also a p was known. But I want to emphasize, to look at the epsilon. The dependence on epsilon is much better.
But this is not the special case, right? You're talking about embedding of LP in AP, and now we are talking about embedding of L2 in AP.
In LP.
Who's
Yeah.
the subspace?
It's a special subspace. Okay? So I'm saying even for this special subspace that was, most of the interest was concentrated on it, even for that there is something new here. So for that, this was what was known before, and you get an improvement on the dependence on epsilon, which is something that personally interests me because the dependence on epsilon Dvoretzky theorem is something I worked on. So it becomes really almost a constant when p is large. Okay, and even so as I said, for p equals 4, it's not an improvement because there is an isometric embedding. But for p equals 6, it's already an improvement. Actually, it was known before that you could remove the square here, but this is another thing I noticed once, and it's not published anywhere. But this is much better even for p equals 6. You get 2/3. Okay, so I don't know, and I wonder what is the right thing here. It maybe it indicates that this
Anyway, the exponent epsilon.
4 over p.
The exponent 4.
Yeah, this is what I get. Okay. Okay, so this is just something else. Okay, so now let me describe the proof. And the main point is, the main new ingredient here is not my theorem, but the theorem of Batson, Stillman, and Srivastava, so people in computer science. So let me state their theorem. So this is this is 2009, so it's quite recent. And I'll state it like that. So you have a positive definite matrix. K by K, positive definite matrix. So of course, anything like that can be written as I'm talking about symmetric matrices. I know that for most of you, positive definite is always symmetric, but so it can be written, any matrix like that can be written as a sum of, I'll write it like that, VI for some vectors VI, some M, okay? So VI for me are K by 1 vectors. They're always so this of course in functional analysis notation or algebraic notation, this is VI tensor V. This is the operator VI tensor VI. Okay, so any positive definite matrix can be written like that in many different ways usually. And the theorem is that you can reduce this M to be basically K without changing the inner product introduced by A, or almost do not change it. So there exists a positive, non-negative. There exists SI non-negative, I 1 to M, and only at most K over epsilon square of which are non-zero, such that if you look at another positive definite matrix, this one, so such that putting A tilde to be sum of SI, AI xt. So now I'm writing still I going from 1 to m, but there are actually only basically k.
These are V's, not A's, but V's. The A's that you just wrote, they should be.
VI. So there are basically only, well, k over epsilon, exactly k over epsilon squared. This should be, if you want to be precise, it's upper ceiling of that. So it's another matrix, but there are only k over epsilon squared elements in its representation. So it's another positive definite matrix. And if you look at A tilde xx, how do I write it? Let me write it in algebraic notation. So this is smaller equals than 1 plus epsilon squared xt ax, and larger equals than 1 minus epsilon squared. I'm doing it even with a precise constant. I'm writing exactly what we got. Okay, this is true for every x in Rk. Okay, so the norm given by A and by A tilde are basically the same, even though A tilde is represented by much fewer vectors. Now, the reason they did it is because they were interested in graphs, and what's called they wanted to find specifiers or edge specifiers. So I'll begin to run out of time. I thought that I have plenty of time. So I'll be very quickly. When you have a graph on with vertices and edges, and a weighted graph, okay, with weights on the edges, W. I don't know if you write it like that, but so you don't really need the edges. I mean, some of the weights may be 0. And you look at its Laplacian, which is so this is the operator which is let me call it L. X is sum of W u v x u minus x v square. These are the weights, yeah. Over all u v, or if you want over all edges u v. This is a Laplacian. Maybe you're not all familiar with it. If you're talking about a graph with a regular graph with degree d, then this is just d times the identity. L is just d times the identity minus the adjacency matrix. Okay. So of course this is something that is very well studied in computer science for reasons that I'll say in a minute. And this is positive definite. So and what this thing says is that that you can find so you can apply this theorem for L, and what it turns out to be, I don't have much time to do that. I'm sure that most of you know it better than me. Then if you look at the L tilde corresponding to it, then this L tilde is a Laplacian of another graph on the same vertex set, but with different weights related to this S either. So there is some other graph G prime, which is on the same vertex set, but with different weights, and only it will be, I didn't say what is the size of it, but the size of these, let me call it K. So only K over epsilon square non-zero weights. So if you want only K over epsilon square edges, yeah, and you get the same inequality. Well, it's an inequality x. So maybe I'll write it with this. So sum of W u v x u minus x v square is almost as well up to this quantity is the same as sum with the W prime. This is what comes out from. Okay, now why is this important in computer science? Is because you now take so this is true for every vector x indexed by the vertices. But take a vector which is, so you have a graph, and you have a subset S. Take the vector which is 1 here and 0 here. Okay, the components are 1 for u in S and 0 for u not in S. Then what you get is, so then this is most, I mean, if u in V are in S or both are in the complement, this is 0. And if not, then this is 1. So what this counts is a cut exactly, the value of the cut. You know, you only look at edges which crosses from S to the complement of S, multiply them by the weight and sum it up. This is what this thing is. And this thing is the same thing for the other graph. And what this thing says is that you can find a graph which usually with much less edges, with number of edges is proportional to the number of vertices, which have the same cuts. For all cuts are, well, up to this quantity, all cuts are the same. And of course, this is something which is important in many situations. In particular, if you start with a complete graph on k vertices, then you find something which is like an expander. So it is a graph with only linear number of edges, which has the same expansion as a complete graph. So it is an expander. Now, of course, doesn't have a constant degree, or it is not regular, but it has average degree a constant. And also, it's a weighted graph. Okay, but of course, this is just a special case. The nice thing is that you can do it for any graph. Okay, now what is the relation between this theorem and what? So how do you prove the theorem that's stated there? The first thing is to write this theorem of Batson's, Srivastava and Spillman and Srivastava in a different way, which I thought that I'll have time to do, but I will not. But it's kind of elementary. So it may be even written in their paper, I don't remember really, but it's completely elementary what I'm saying. But so this implies the following, that if X is a subspace of L2 M, I think M is the number, L2M of dimension K, then there are weights at most, as before, at most K over epsilon of which are non-zero, such that the following happens. You look at so what I'm interested really is the SI X, like X of I. So so for X in X, or for, I'll write it as X of 1, X of 2. I prefer to write like that for, well, because I use other notation for something else. So these are just a component of the vector. If you look at this square, this is equivalent to the original thing. And up to 1 plus epsilon over 1 minus epsilon square, the same thing as before. This, of course, is just the norm of X squared. Okay, so what does it say? It says that you have kind of sampling. I mean, you sample the I's, weighted sampling, I would say. Okay, you pick up only the I's for which SI is not 0, and for this one you put some weight. But after you do it, the L2 norm of what you got, so this is a weighted L2 norm, but it's of course isometric. The space that you get is isometric to L2 of the dimension. Is equivalent to the norm. This is very similar to what I said before with the sampling only in L2. Of course, in L2, all these things are, there's no point to do all these the things that I wrote here before. Every subspace, k-dimensional subspace of L2 embeds in L2k actually is equal to L2k. So, but the point here is that you can achieve basically the same, or actually a weaker result by sampling in L2. Looks not related maybe to what I'm doing. Okay, but from that it follows very easy, that this thing follows quite easily. So first of all, to show this implication, this is completely elementary. I mean, you just have to sit and write down exactly what it means. And actually it's equivalent to BSS. I should say also before I continue that the theorem of Weizmann, Spielmann, and Srivastava already had applications in functional analysis before actually they found applications in functional analysis. Maybe I should say something about the history, especially if you look at it like that. Then something like that was known before, except that the dimension had an extra log. This is due to Rudelson in his thesis, actually. And it's related to kind of getting a joint decomposition with few vectors or something like that. And the thing that they did first, I don't know if all of them, but certainly Spielmann, I think Spielmann and Teng, I'm not completely sure. They used the result of Rudelson to get something such a specifier, but of course with more edges, a little bit more edges with the log factor there. And after a while, they managed to prove this, and using this, one can now improve Rudelson result to remove the log k from Rudelson result. I didn't say exactly what Rudelson result is, but so this is one application. They have another application to invertibility of restricted invertibility of matrices. This is related to work of Bourgain and Safriri. And there are now at least two other applications. So this is one of them, and the other one is the thing of Newman and Rabinovich. Okay, so how do you get this thing? So I want to prove this theorem there. So I have a subspace of, take a subspace of, okay, so I have a finite dimensional subspace of LP. And I can always, as I said before, I can always view it as a finite dimensional subspace of some LPM. I prefer to write RM because I don't want to, RM with LP norm if you want, or whatever. Okay, by a small approximation here, but I'm allowing a small approximation. So I'm viewing it as if it is a subspace of just LPM. And then what I do is I look at the following subspace Y, is the space of all things of the form. I write it as Y is equal to x1 circle dot x2 circle dot x p over 2. I take p, so p is an even integer. I look at p over 2 copies of x and took vectors from each of them. The xi's are vectors in x, and multiply them pointwise, multiply the coordinates, okay? So this is my notation for multiplying the coordinate. The first coordinate of z is just the first coordinate of z as the first coordinate of z. Very simple multiplication, kind of kindergarten multiplication, okay? Just pointwise multiplication. Is it clear what y is? Okay, so I'll speak in a minute about the dimension of y, but certainly the dimension of y is smaller or equal than k to the p over 2. This is trivial, I mean, but there is actually a better estimate. I'll say it in a minute. But let's just take this just to show the idea.
So why is the span of all this?
Excuse me?
Why is the span of all this?
I'm sorry. Why is the span of all this, right? This is not but the way I wrote it, it's not a subspace. A basis is just, well, I'll speak about it better. And I'm going to apply the theorem that I'm just erasing, not the theorem, the corollary of it that I wrote there, to y, not to x, but to y. So there exist SIs, I from 1 to m, non-negative, at most. How many? So I have the dimension is k to the p over 2 over epsilon square, of which are not 0, such that what do I get? Such that I have this thing in L2. So what is written here is that sum of SI y of I, this is why I change the coordinate of y is basically the same as sum of yi squared. Now I apply it only for very special vectors, so the vector of the kind x multiplied with itself, p over 2 times. So when you apply to this thing, you get si. This thing is just the I coordinate of y, is just the I coordinate of x raised to the p over 2. So you get, and then there is another square here, so you get xi to the p. The equivalent in here is the same, which is of course the LP norm to the p of the original vector. And this, and remember, only that many of the si's are not 0, so you get an embedding of LP into LP of z dimension. Okay, and the constant turns out to be, well, something related to, I raised everything, well, the constant is, I will not talk about the constant. You have to be a little bit more careful if you want to get the results that I stated, but from that you get already this thing, okay? No, exactly, you get k choose p over 2, k plus p over 2 minus 1, I think, choose p over 2. This is a kind of the classical thing, it's a nice thing to prove. So what do I need? I don't need really this subspace, but any subspace containing all of these vectors is okay. So you take the space of all homogeneous polynomials of degree p over 2 in variables from x, and it's a nice proof to, it's a nice exercise to compute the dimension of it. It's very simple, but kind of by induction. And what you get really is a k, I think k plus p over 2 minus 1 over p over 2. Is that right? No, you should know this, right? And you do that, and you also have to be a little bit more careful with epsilon somewhere, but I will not do it. This is our idea. So I see I'll not have time to talk about this thing of Newman and Rabinovich, but I'll stop here.
Questions?
Can you say, I mean, what happens for the L1 problem, the linear, not the linear version? Like, just is there some obstacle, or is it just there's no way to start? Or?
Well, it's clear that with sampling you cannot get better than k, and with sampling like that you can get k now. And actually, you can get, if you are allowed a large constant, then you can even go below.
No, but I mean the linear version for subspaces of L1.
Oh, what is the obstacle? Again, the obstacle is, okay, so let me tell you what is the obstacle for.
So I mean the obstacle given BSS. So the sampling is obviously an obstacle.
What you want is, you see, what you want is really to prove the same thing with the L1 norm here instead of the L2 norm. I don't know how to do it. I mean, the proof uses very heavily L2, uses positive definite matrices, computation of eigenvalues, things like that, I mean, which are not available. It's actually not hard, the thing, but I don't know how to do it in L1 I was trying, I can tell you that. I'm still trying, but it needs a new idea, it's clear, but there is some, maybe what they have is kind of a guideline of what one needs to do. This is what I'm trying to do. Yeah.
For non-integer p, probably is really right.
Yeah, for odd, the problem is, you see that you take here the actual powers, not the powers of the absolute values. If you take just the actual powers, then there is a subspace, I think, of half the dimension on which everything is 0. So, this is, so you can state it as a similar theorem, but it's not, I don't know, not an embedding theorem.
Okay, so thanks again.